singularity time, there's the Planck time. Both of these are essentially outside of the universe because the universe is basically the place where space-time exists. So space-time is where, again, all the forces and the laws of nature exist upon, and that where we have a broken symmetry between matter and antimatter, and that this broken symmetry exists is where we live. However, theoretical physics also relates everything back to a supersymmetry in which guide them in all the mathematics that describe fundamental reality. Now, in the nature of life, if we look at that, there's a difference between the physics and mathematics and life. And for example, a theoretical physicist, Brian Greene, basically commented on that when asking about aspects of consciousness and life. He basically said he didn't have much to say about it because his realm is on the physics and the smaller things that are absolute and are more simple, whereas life and mind are extremely more complicated. So he said generally, for his group of people, that they basically, if they don't talk about consciousness, life, and the mind, because basically those are like too complicated, and so anybody that is in the right mind who is a theoretical physicist or mathematician doesn't talk about those things because they don't have anything to say about it in general. However, in T-theory is a total theory of everything, in the sense it's total time theory, in which it's going to try to provide some of the whys in which theoretical physics and these people don't deal with, and how they're possible relationships. So I am delving into life today, in which kind of describe the concept of where life comes from. In general, I've mentioned T, which stands for timeless energy access. So the flux or the flow of energy in life has to do with its breaking of symmetry, which T-theory predicts. And this happened at the Big Bang. However, the singularity didn't just leave us. It just broke symmetry a little bit, in such that this singularity actually exists in front of us in time today, so that the fundamental concept in T-theory that everything has to be related back to is the Planck sphere. And the Planck sphere is where the singularity first comes into existence. We broke symmetry, and then after we broke symmetry, here's space-time, and then say, basically all the laws, the forces and laws that exist in nature come here. Well, in life, there's two types of life in T-theory. There's kind of what you call inorganic life and organic life. And the concept of inorganic life is the concept of stability of atoms. Like, for example, we have the proton, which has three different quarks in it. Those quarks are confined. In other words, the mass of the quarks themselves are essentially massless or close to massless, and the energy of the energy of the proton itself is based upon the confinement of the proton. So here's a physical thing. So in some way, there's a continual movement of energy on the fundamental levels of what life exists for matter. So if we're inorganic life, it's just talking about, this could be a single hydrogen atom in which we have the electron floating out here. Now the thing about life in the simple hydrogen atom, now again we'd have the confinement of which is actually an acceleration, a force that's confining these quarks. So there's movement there. So there's movement of energy there, as well as the electrons going around the atom. Although in T-theory this is not actually a cyclic thing, but rather it would appear as kind of dots and points at different things, because it has to do with waves. And the waves could, the collapse of the wave function would cause the electron to be almost anywhere in here, although it may be in an orbital. Now, remember that electron's moving, so there's life in motion. There's motion in the electron to begin with. There's life in motion in confining the proton, and that these again this hydrogen atom would have different levels where the electron exists upon, and of course Bohr defined a lot of this concepts of these orbitals, in the original atom. So in the sense of just plain inorganic life, there's the concept of there's movement going on. There's also confinement of the electron to a certain degree in which it has certain orbitals it can exist in, and that's the quantum jump is that it only can exist at certain levels, and yet the electron is also an energy transduction. The atom is an energy transduction. It's like a sense where it can transduce energy, so that basically if I have an electron here, it automatically has a tendency to want to go towards the proton, because the proton is a positive charge, and so there's a force pulling it down. Of course, when the electron drops, that's what a lot of times when we generate a wave. So the idea, there's a lot of motion at the subatomic level, in which that's kind of inorganic life, in the sense that there's some things like for example, David Gross was involved as an example, and I can't remember his partner, but at the moment. But anyway, he was involved in the idea of quantum chromodynamics, which basically described the strong force, which is what we're talking about here, the confinement of the quarks inside the proton. Now remember, if we're going back to T-theory, even smaller than this is the Planck sphere, because we're talking about, this is somewhere about 10 probably to about the, I don't know, 10 to the minus 17th or 8, of centimeters, and this is 10 to the minus 33 centimeters. So in some way there's almost like 20 orders of magnitude or so in the size of a proton versus the quark, versus the Planck sphere. So so there's a distance between where the forces exist here at the Planck level versus where the forces exist here at the proton, as well as, when we're talking about the strong nuclear force, we also have to consider in larger atoms, like we have the periodic table in which we have multiple protons and neutrons within an atom. There has to be other forces in there, because it's not just the confinement of the quarks, because if you have another proton in here, there's another plus charge in here, in which, if this is now helium, and there's 2 electrons on here, these 2 will want to push away from each other, because we know about the concept of, pushing the forces, a positive will push a force. So there has to be something holding these protons in, as well as there's usually neutrons in there. So in the concept of things tend to want to go towards, in close proximity, randomness wants to push everything away. The gas molecules, things want to push away. So when we talk about the protons of atoms that were in the periodic table, we're increasing numbers and numbers of these protons, and there's a continual confinement not only of the quarks inside each proton and neutron, but also confinement of all the molecules there. So there's multiple forces really kind of going on to hold the nucleus together as a function, and these are continually being implemented, such as the idea of string theory is that this Planck sphere, this Planck sphere would be at the very center of all these things. The Planck sphere would be at the center of a quark, it'd be at the center of an electron. So the idea that there's a distance, and that distance then comes further out where we have these forces, and that in T-theory it's actually the singularity inside of here that is providing the unification of all the forces, in which there's an acceleration of energy occurring. And that's the idea in T-theory. So everything has to relate back to this fundamental concept of space-time, the idea of these fundamental forces that are underlie, that maintain stability over and in time. So there's like a dynamic stability dynamic stability that is fundamental to life, whether it's inorganic life of just the molecules, or whether it's a cell in the body in which, and us as human beings, that everything's being replaced ultimately, whether it's the cell membrane, or whether it's proteins in the membrane, or whether it's the DNA itself is actually being turned over and reformed. So the proteins in our body, that if something's making a protein, those are continually being made. So there's the idea of, we both have a physical existence in life as a physical form, but we're constantly being formed and broken down, formed and broken down. So the idea here is that fundamentally, if we go to the physics and mathematics at the simple levels now, the proton of the hydrogen helium atom, which Bohr described, can be kind of explained to a certain degree. However, as we get to larger atoms, it gets more obviously complicated. And then, of course, we're talking about not just larger atoms, but now we're multiple molecules. We have a multi-carbon compound. These bonds here are based upon the bonding of electrons in these kind of spheres of orbits. And then if we have double bonds, we have different bonds going on in different ways. So the idea here is that in relative distance from the Planck range, there's a 20 orders magnitude to the proton or so. And of course, as we go further out, then we're going to have other molecules. In other words, in T-theory, there's multiple forces, which was, as I was trying to get at, is that there's multiple forces in just the proton. The strong nuclear forces actually would be a combination of forces, the ones that actually hold the quarks inside of the proton, but then also the ones that hold the protons, the ones that would want to push away from each other, as well as the neutrons, as a collection which is holding them all together. They combine into one force, but in reality, or in T-theory, there have to be multiple forces going on inside of that realm. As well as we get to the larger molecules, there's the forces that cause chemistry to happen, in which certain things are going to combine in a certain way. If I have this molecule here, there's forces not only between the atoms, so there has to be forces that hold that stability of those bonds, and those are continually being formed and broken down, just as the strong nuclear force is being formed right now. And in the concept of the wave function, if relative fundamentally is the wave function, then in one cycle of the wave function, that's where a new past now has to have the forces all embedded in it, as well as the new now coming in. So there's now a time period in which there's energy in here, but it's not at a, like if these are particles inside this wave, then they don't become physical until the wave collapses. However, the probability of that particle being in here is over a certain region, so it's not in a particular point. And again, things are relative to the quantum. Like Einstein said, if we're sitting at the quantum realm, then space-time is not definite. It is kind of garbled, and because everything's on a wave function. However, if we're sitting in our dimension of being at way outside of where matter exists, like say a meter or two, then this is going to appear, if this is inside an atom, as possibly a proton. And then again, in string theory is the idea in which these strings of both the closed string and open string are actually sitting outside of the Planck sphere, just outside. So there's this resonance, theoretically, that again in string theory would be the vibration of these waves which form a symphony of particles. So underneath everything of physicality, of inorganic life, is there's a life in there in which things are moving, existing. And then as we move up in the sense of now we have molecules because of the forces bonding them, but not only those molecules have to maybe involved in, say if it's a protein, these could be amino acids, and the amino acids are all constructed together, in which kind of in a bead, a line which the amino acid is the bead, in between are the bonds in between the atoms, and then this thing folds up, and then what T-theory is also proposing is that even the folding up of the protein is going to have to do with space-time, the existence of space-time, and the forces that are embedded. And that would be, again, the stability of the mathematics, the dynamic stability of space-time, such as the cosmological constant that would provide a certain amount of energy per cubic meter of space-time. In other words, also supplies the lattice work, the stability lattice work of space-time, in which the laws of physics on a fundamental level, such as 2 plus 3 equals 5, the number stays stable from the beginning of the breaking of symmetry at the Big Bang. These numbers stay stable. The equation, the relationship all stays stable. So that on the physics level, on mathematics, there's predeterminism in the sense that if they look at this from their view, everything's predetermined in the sense that these mathematical laws all make a symmetry and make sense. And so when we're talking about the idea of free will and things like that, their view of, from a strictly mathematical physics kind of point of view, there is no free will. Everything is predetermined. All the mathematics make sense. But however, that may be true on a small fundamental level of the scale. However, the nature of life is different, in which we actually have greater efficiency. In other words, in physics we have entropy that's causing continual randomness throughout is continuing. However, when we look at life, life is the opposite of randomness in the sense that it is where energy actually came together, became more functional, more relationships to symmetry. When we see a human being, we see symmetry. They have 2 eyes, 2 arms. There's a symmetry related to them physically, and as well as all the physicality that we have is based upon the mathematics of symmetry. So underneath everything is a symmetry. However, life itself is more efficient, and in the sense of that, if we're related to special relativity, if we're being accelerated, in other words, the idea is that fundamentally we're all being accelerated by the singularity, supersymmetric singularity, and that's why we have this access to the singularity, such that the reason why the electron doesn't implode onto the proton is because the electron's continually being accelerated conceptually, so that it always has it's not going into the nucleus, as well as the nucleus itself is being accelerated in the sense of being pulled together to find the quarks. So behind everything is an acceleration of energy, and so we have forces in life. So in other words, the life force would also possibly be related to an acceleration behind it. And of course, the folding and fundamental ground states of not only just atoms and structure would be due to a fundamental force, such that some people think of the ground state as being the lowest energy state. In T-theory, it's actually a higher energy state because everything's heading towards the ground state, whether it's a protein folding into its natural ground state functional activity, in which it may have 1,000 or thousands of ways it could fold. It folds fundamentally into its most active and efficient energy form based upon the concept of that the ground state is more energy ordered state, and that forces are embedded in space-time that are not only at a distance from the Planck sphere, but also tinier than we can see, but embedded in space-time are the laws and the constants of these forces that are fundamental and continually being created and formed at each moment, and stable at the same time. So there's a dynamic stability underlying all the forces, whether it's the Higgs field that permeates all space. This is the same concept that in the Planck sphere, is that that within a certain period of time, just outside the Planck sphere, so here's the Planck sphere, singularity, and then space-time. In here are the forces of nature, but those forces continue to go out, not only just for the fundamental of atoms, but also to the complexity of molecules binding with their bonds, as well as to the conformation of proteins, to the efficiency of organ systems and how they interrelate to each organ, and then how they fundamentally relate to a whole species or being, and then of course usually through the brain and then through us, through the mind, we have an additional connection to these forces. So there's kind of a distance in the sense of forces in space-time that hold the stability. And so the life force, along with it, so you have inorganic life, but you also have organic life. And of course, cell is the most simple form of an organic life. Okay, so going to continue here further now. In the sense of, we talked about everything's related in T-theory to what is the single thing in the universe is the energy. And again, in T-theory, it's the acceleration of energy inside the singularity that's supplying the energy for the dark energy of the expansion of the universe, as well as all the fundamental forces that drive all these forces, whether it's the nucleus to, again, chemical bonds, and then to folding of proteins to, organ systems, and then organ systems where they're maintaining certain levels of concentrations of elements of energy inside the cells and so forth, that there's this continual force being applied throughout everything, that it kind of, there's a dynamic flux, an energy flux going through everything. Everything physical has an energy flux through it, so to a certain degree we're processors in which energy is passing through us, both from the inside out as well as our senses are coming in. We have energy senses, such that the next kind of topic is the concept of energy senses. So that the idea is how we sense life and how we know that life exists is that we have an energy transduction system, because in thermodynamic laws, their energy cannot be created nor destroyed. It can be transformed. So that comes into the concept of senses. So the idea is that space-time, in some regards, is kind of like a sense in the aspect. It's kind of like our skin. Space-time, that our skin is a membrane which we can have heat and cold, and in other words, it kind of represents in which heat would be adding energy to our system and cold would be extracting energy from our system, and so we have a sense of that. So that's an energy flow, as well as if we have light coming in, we have the eyes that can sense the light. If we have sound, we have ears in which we can sense that. Again, if we have a nose, then we have air molecules. So everything's related to the concept of energy and the energy transduction, and that's where senses come in. So that when you have a sense of something, well, then you're going to have an energy transduction system, whether it's the atom itself having the proton and the electron out here orbiting. You have an energy transduction system in which if a photon comes in here, that photon can be absorbed by the atom. It excites the electron, so it has energy transduction now, and then the electron's out here and it has more energy relative to the nucleus. And of course, as the electron drops down, then it may release another wavelength out there. So that's energy transduction. Or if this becomes excited due to thermal properties, again, it can be excited, and the idea is that there's this energy flux going on, and there's also in this flux both a push in the flux and a pull in the flux, and that is all related back again to the singularity, in which the pull would be again the acceleration of energy, and the push would be the creation of energy. And that's why maybe empty space, empty space has molecules both appearing out of it. It's dynamically active. There you can see things coming apart and then reforming back together. So the idea is that there's this continual push and pull of things happening in active space-time. So underneath that, again, T-theory would say would be the singularities. So everything has to relate back to the central concept for everything. Now, when we're talking about, again, senses, we have these senses where we're energy transduction. Well, likewise, our senses are with our mind, in the sense that our mind is an adaptable sense receptor in which we can decide what kind of sense it's going to be. If it's this sense for biology, then we study biology and we learn the nature of how senses work in biology. If it's the sense of mathematics, well, then we sense the energy of the relationships of mathematics. So that, again, the 2 + 3 = 5, that we sense that energy dimensions and the functionality of that. So couple thing with energy is not, we have energy in flux, and we can have different energy levels where the energy can be more dense, or the energy can flow through something faster, or the port of the energy can get bigger so more energy flows through it, or the embedment of information, or again the density of the energy could be more mathematically and symmetrically tuned to be balanced. So that the idea is that there's always this flux of energy continually going on. And when we talk about the universe, the universe didn't work because we made the universe. So the work was equal to a force times a distance, and that force, the distance in this thing is going to be the Planck distance, Planck length, and the force is going to be basically caused by the singularity. However, it's broken distance, so we have now the timeless energy access, which gives us the work of the universe, which is forming the universe. And if we also took this concept of force, and the force would also be equal to the work divided by the distance, and of course in the concept of this is that the smaller the distance where we have, so the distance of protons is a lot smaller than the distance that I am, so therefore there's more work and forces involved in small things rather than in big things. There's more work to hold the protons together, and the strong nuclear force, and the work even higher to separate and break the symmetry is going to be a lot higher work than because of the distance is so small. There's more work and more force involved in that. So just kind of understanding the relationship of, again, all our mathematics, from classical mathematics to general relativity to special relativity to quantum mechanics, are all mathematics that should fundamentally describe everything underneath it. But then we come up with the concept of life, and life is basically an acceleration of energy in this regard, in the sense that, again, that for like say we have an enzyme. Now the enzyme in life, like if we have sugar, we have glucose, and if we go by traditional physics and science and chemistry and life, that glucose will break down to CO2 and water over hundreds of years or so forth. But it will take that time, a long time, to do that, where the nature of life is that we can form a protein, and that protein has a certain structure which now has higher density and information and relationships, that it can actually expedite this breakdown, so that shortens the time and increases the density of energy in a shorter period of time, and then time will change. Again, it would be relative to the enzyme. Time it'll take to break it down will be a lot shorter time because the energy of the enzyme gives it greater functionality to break it down. So life has a greater efficiency with energy. And that's a key thing here, because even at the nuclear level, where we're actually, when we divide the cell, there's a reduplication. When each cell divides, it has to reduplicate the DNA. And in the process of making that DNA, we have all these systems in which there's errors in the coding of the DNA, but we have such an efficient system that we end up with a very small error rate, and that efficiency of reduplicating that DNA is not what would follow typical randomness. And so there is an ordering or convergence and ordering continually going on, which is our forces in the concept of T-theory that are embedded inside of the space-time membrane at these different scale levels removed from the Planck sphere in distance. So that inside of space-time is our forces that causes protein to fold naturally. Now, this was shown in an experiment where they took a protein inside the cell, and a lot of times they figure, well, these proteins fold up because of their environment inside the cell, because you have the nucleus, and the protein may fold up naturally in here, but the cell has a certain isotonicity, it has positive, negative proteins, and it has other folding, little membranes and things that help fold the proteins, and the internal environment that it's in. And they said, well, the folding of the protein is due to that. But they did an experiment where they took a protein out. Now, a protein obviously has different amino acids, and the folding, because of the order, this can fold in any shape. There's maybe hundreds of thousands of ways it could fold. Yet there's going to be one that has the confirmation for activity, for existing and for life, so that there'll be the fundamental ground state, or the one that has the most activity. Now, what they did is they took it out of the cell, and they observed that this folded. Now, this may take to fold into the normal. It'll be like the lottery of, how could this fold randomly over in time? It would take, 100,000 years to fold into the accurate protein that had the most activity. But they noticed that if we take it out of the cell and actually put it in, say, just a solution that obviously can allow the protein to exist, it folded innately on its own. So that experiment alone kind of drove in my mind that the forces of nature are embedded in space-time, and they're an addition causing for the greater functionality of things. So the dimensions of space-time, where we currently have 10 plus 1, they say, of space-time dimensions, basically represent dimensions of functionality, such that the relationships of these things have it and the symmetry and the relationships to functionality all are deal with these multiple dimensions in themselves. So the dimension, even though we're three-dimensional in a physical realm, the atom itself represents a 10-dimensional functional realm. So the idea here is that the nature of life is that this enzyme could break down this thing in shorter time. Greater density of energy is released, and again, the distance to get to the breakdown is shorter. So these are all kind of like the gravity of the full pulling together and the ordering and the convergence of the protein to cause that efficiency is due to pull forces. So the pull forces, again, life forces, are causing the functionality to increase. So we observe greater functionality in life, so that there are forces in fundamental space-time that deal with the ordering and the functionality of life. And then it's up to our senses, the sense of being able to take the need, like on the outside of a cell, we have maybe thousands of senses So it's not like the smaller we get, we actually have more senses going on, rather than, the eyes and the ears we think are fundamental senses. But here you're going to have a sense for maybe bringing glucose into the cell when it needs it for energy. Another sense is going to be telling it that there's some bad molecules on the outside, and to maybe make more proteins for this way. Another one's going to say, I need proteins to move, so there's going to have scaffolding proteins, and so that these are receiving multiple energy senses from all, if it's in an organ or whatever, it'll be receiving multiple inputs from a lot of different sources, and those energies are combined into obviously the DNA helps read the proteins, which give it the physical structure, but there also is a point where, just like an airplane, we can supply all the parts to the airplane, and we might have the DNA may give us the diagram, all the information how all those parts fit together, but all the parts in themselves coming together to make the airplane doesn't make the airplane fly. And the idea is there's a life force or a force beyond that causes the plane to fly, which usually is driven by, in T theory, the intention to fly was what drives the building of the plane and putting the plane together. So fundamentally there's a force or a sense. Now if we sense that intentionality, there's going to be a sense receptor to that intention, and then thus we must have a sense receptor for that intention inside of our minds. So part of the nature of life, what is fundamental to all living things in physicality, is the sense to be, to be alive, the sense for survival. Whether it's the inorganic way of just the forces being there, continually existing over every single moment of time, or whether it's a animal or a species trying to survive, or a cell trying to survive, the mechanism, human beings have the consciousness, but fundamentally everything has the intention to survive. So the nature of life fundamentally has to be driven by the intent for survival, or this fundamental forces, which would be embedded also in space-time. In the aspects of understanding fundamental chemistry, we've all heard of the periodic table, that kind of the idea of inorganic life, I guess you'd say. The periodic table in which we have all these atoms that have come up, and of course the idea from cosmology and that sense is that a lot of these atoms were made inside stars, in which when the stars collapsed, they pushed all the the protons and electrons together, which caused the merging of nucleosynthesis and so forth, creating more atoms, and the atoms that we see today with the periodic table. And of course that process would be enhanced by space-time allowing for all the forces. If you push the atoms together, then the forces of combination, if they're inside of space-time, would allow for the multiple protons to come into that force field range, so that they could then stick and stay there. So the idea is that once you've compressed them in to create a larger atomic molecule as far as the number of protons, then the force fields are already there, present in time, to cause those things to stay stable, along with the chemical bonds between the atoms now. So that even goes out further, so that again, the nature of life is going to be the carbon bonds, the electron fields that are binding the carbons, and so there's force fields involved in this area, as well as again force fields causing the again, if this is a protein, for that to come into order. Now we talked about the periodic table allows for the atoms to become stable, but also just in the genetic code there's another periodic table, in the sense that we have you've heard of codons. Codon is where they have basically 3 letters of the say 3 letters of the DNA. So you have uracil, a guanine, and a adenine. These all represent a reference to an amino acid that are associated, so that we have these what's called transfer RNAs that allow for these kind of codons to exist. Where, and again, this is related to a DNA molecule, which it has again a ATCG. Submit this, so, and this is inside the nucleus, and then these things get duplicated, right, through replication, and then but at the same time, each time there's a 3-piece of the DNA that represents a letter, so to speak. Again, a physical nature of an amino acid. So there's this like periodic table for the amino acids to the DNA that also kind of exists. There's this energy transduction system again, where there's a relationship between the DNA and the order of the codons and what they say. Now this may be a stop codon, which would tell the reading of the DNA to stop. We also have initiation codons, which tell this is where you start reading the DNA. So the idea is that there's all this kind of regulation, but also energy transduction, in which then now through taking these, and this would be the RNA, basically here, this would be you have messenger RNA, which would be how it's represented as it goes out into the cytoplasm from the nucleus. And then the transfer RNA are these relationships of these molecules that have these codons relative to the amino acids of the transfer RNA, and then from there they go to the ribosomes, and the ribosomes will go ahead and read off these transcripts and create your protein of different amino acids in a chain, which then have the functionality that they do. So the idea there's this continual energy transduction system going on in life, and then it's the dynamic stability of the system, a control of the system to keep it in order. So the idea is that in life there's this randomness, that entropy, which agrees in physics. However, that entropy is maybe beneficial for the diversity, but fundamentally underneath it are constants and ordering and structuring things for the self-assimilation of the universe, such that there's self-assembly going on, and those forces are also within the space-time membrane in T theory. So that, again, even the stability of the replication of the DNA, I said, had a very low error rate, so that, again, energetically, we do things very efficient. So if life is to represent what fundamentally space-time is, if we're a representation of life, then in the theory of a total theory of everything and the picture of the reality, there has to be a functional efficiency with it, with the energy, such that T theory predicts a dualiverse. In this dualiverse, the fundamental forces are all related to the singularity. In a multiverse that's currently predicted by the possibility of string theory, in which 10 to the 500 universes, this would be extremely inefficient energy network. Would not make sense for individual universes have their own individual forces and systems. It's total energy inefficiency. It's not what we observe in life, which is energy efficiency. In T theory, again, that 10 to the 500 universes as predicted in string theory is actually inside of the singularity, the gravitational, the single gravitational pull of everything that's inside. That represents our potential. The potential for everything is 10 to the 500 universes, although 3 space-time dimensions broke symmetry, which created our Dualiverse. And now I'm going to just kind of move to about the nature of life. I said, what is the single thing in the universe is energy. So everything has to go back to energy. And so when we talk about energy, we're going to now go into some biochemistry and kind of look at that a little bit more, or the energy generating aspects of the cell itself, because on a single level the single living thing of life, for life is a cell. That would be the smallest unit of life, would be the cell, and the cell has to get energy to make energy. So how does it kind of do that? Now that in the cell we have different things that are important energy wise, and one of them is ATP. You've heard about that, I'm sure. Adenosine triphosphate. It's basically the phosphates have a lot of the energy with it, but it's also made of part of the DNA structure, adenosine or adenine. But also they have these other molecules called NAD, H, and FAD, H2. So the idea is that there's these molecules that are involved in the energy for keeping a cell alive. Remember now, the ATP is a high energy construct in which the ATP helps with the synthesis of proteins, lipids, and amino acids, so that energy needs to be generated based upon the formation of that. And these are molecules that basically transfer the energy around in the cell to a certain degree, and these both lead to the production of the ATP. You may have heard of the electron transport chain. So that's, say, in the mitochondria. Say this is mitochondria. This is not of scale, but in the mitochondria, basically, we have the electron transport chain where we have oxygen being, quote, broken down to H2O. Now, in the process, there are electrons that are being transferred down this chain, and these are the carriers of the electrons in the cell. So what happens in the cell is that how we get energy is we have, say, a glucose molecule will come into the cell. Now, say this is the cell membrane, that in order to keep it in, it actually gets phosphorylated. So now that has a glucose phosphate on it. So the phosphate has a charge, and that charge helps now keep the molecule inside the cell. So, and then what glucose does is basically we break it down. When we break it down, basically we first transform it and transduce it through a bunch of enzymes. We change the order of the molecules a little bit. There's still 6 carbons, and at some point it splits it into 2 3-carbon units. So there's 2 3-carbon units, and those 3 carbon units can ultimately end up going into what's called the mitochondria. So the idea is that in the process of breaking this down smaller, we're breaking bonds. There may be an ATP or GTP is another form of energy that comes off, but also one of these molecules, like an NAD, will form, an NADH, and this actually has combined with it electrons. So how it's getting electrons is basically, it's stripping it from the bonds. So the bonds of chemistry, between a carbon-carbon bond or a carbon-oxygen bond or a carbon-nitrogen bond, these all have energy embedded in them. And in the process, when we break those bonds, say this one, has oxygen, and so that if we break this bond, it may end up being, break that bond, we get the energy from that may be transferred to an ADH, and that NADH makes its way over to the mitochondria, and indirectly it's transferred into the cell, then NADH through a transfer process, which is certain biochemistry, but the idea that NADH then supplies the electrons to this chain, and when it does supply it, ultimately the acceptor of all the electrons is oxygen. So it becomes reduced. It accepts the electrons, becomes reduced, and the process, some molecule out here became oxidized as this became as oxygen became reduced out here. But the idea is that we're trying to make this energy, and this energy is involved again in protein synthesis, in DNA synthesis, and that so that we're continually, there's this force are a flux of energy which is based in electrons that are going from the carbon bonds, carbon-oxygen bonds. Remember, for life we have carbohydrates. That's why we have carbon. We have hydrogen. We have oxygen. Those are the carbohydrates. But then also we have other atoms that are essential for us. Nitrogen, which is involved in amino acids. We also have sulfur, which is involved in disulfide bonds. They're bonding between the proteins, which help with their stability. We have other atoms that are involved in it, but these are a lot of the more common ones that we'd see. And phosphorus, of course, to CHO, and that's where one of them is a pyrophosphate, which when it hydrolyzes, it pulls the energy, it pulls the reactions together. And so a lot of times we have in the body enzymatic reactions, and the enzymes basically, when we talked about A going to and go to B. Now there's different types of reactions in the body, and a lot of times we have kind of equivalents where things can go both ways. And in the body, if we remove this substance, say this is being oxidized, then this concentration decreases and it pulls the reaction this way. So there's some reactions that go both ways, and then there's also reactions that obviously we talked about. Enzymes are almost all involved in the body with making these reactions occur, which would not normally occur if they were outside the body. So the enzymes again are causing greater efficiency of the reactions to occur in either direction. There are some that are more one way in direction, especially if this causes a release of what maybe you call a pyrophosphate, which is two phosphates, and then there's an enzyme that quickly breaks that down into individual phosphates. So, but this is the removal of this product is so quick that it drives the reaction this way. The other thing that drives life and reactions is the release of heat. Now, in the sense of release of heat, in the concept of thermodynamic laws, we have the law, kind of the law that heat goes towards absolute zero. Now, there's an interesting concept for T theory, is that there's this absolute zero point where supposedly things don't get colder then. However, if in T theory